Welcome back everyone, it's Mr. Ordinary here, and we're going to learn a bit about the isosceles triangle theorem. And this is true for every single isosceles triangle that you will ever see. Just a reminder, an isosceles triangle has two sides of equal length. For example, in this triangle you can see that that side is the same as that side, two sides of the same length. And the theorem says that in any isosceles triangle, the base angles are equal. By that I mean the two angles that are touching the equal sides. So there's an equal side and there's another equal side, and these are the two matching angles. Another way of thinking of this, by the way, is that the base angles are the ones that don't touch the apex. The apex is the point or the vertex that the equal sides touch. But I think you can see from the diagram, the base angles are the ones that touch the equal sides. There's an angle there, and there's another angle. These are the base angles. So the isosceles triangle theorem says that these base angles are equal. It also says this other part that we'll touch on later. I'll say it now, but I won't go into it because we'll do it later. The line joining the apex is this point here that touches the two equal sides. The line joining the apex to the midpoint of the base. So the base here is this side, and the midpoint is right in the middle of the base. It does two things. Number one, it meets the base at 90 degrees, so this angle here is 90 degrees. And the other one is that it bisects the vertical angle. And when I say the word bisect, I mean divide into two equal halves. And you can see that this angle here is exactly the same as that one. It's a bit to get your head around, so I'll leave that one for now and focus just on this part. The base angles are equal, and how we can use this to solve some mathematical problems with triangles. As an example, let's look at this one. We want to find x, this angle here, giving brief reasons. Looking at this triangle, what kind of triangle is it? We know that it is an isosceles triangle because it has two equal sides, BC and BA. And because it is an isosceles triangle, this angle here must be the same as that angle there. So if this angle is x, then that angle must also be x. That's what I mean when I say the base angles are equal. So we can give a reason for this. We can state this. We can say that the angle CAB, just to show you what I mean, that is this angle here, this point here, well, not point, that angle. So the angle CAB, from C to A to B, is the same as this angle here, ACB. It's x. And the reason is base angles are equal. That is why I can draw a little x on here to show that these two angles are both the same. Well, now that I know that, I can look at the angles that are in this triangle. Look, I've got an angle of x, x, and 50. If I add up the angles in a triangle, what number will I get? The angles in a triangle always add up to 180. So I can say this plus this plus this equals 180 degrees. In other words, x plus 50 equals 180. And again, I could give a reason, and the reason would be it's the angles in a triangle. Well, now I've got an algebraic equation. Now I can think back to when I solved linear equations in algebra and solve this one. My first step will be to notice that I've got x plus x here. I can simplify x plus x. X plus x is 2x. I can collect like terms. Everything else in the equation I would just copy down. The plus 50, the equals, the 180. That way I have a new equation that is also true. This equation is true. Therefore, this equation is also true. Now, I want to get x by itself. I notice that I have a term here, 2x, and another term here, plus 50, and another term on the other side, 180. I really want this 2x term by itself. I want to get rid of the plus 50. So what I'm going to do is keep all of my letter terms on the left and move all of my number terms to the right. So the 2x is a letter term. It has a letter in it. So I'll keep it here. The plus 50, that's a number term. It doesn't have a letter in it. So I will move the plus 50 to the other side, where it will become negative 50. The equals and the 180 will stay where they are. And now I've got negative 50. Do you notice that I only have number terms on this side now? I've got 180 and negative 50. So this side here, I can actually figure out. I can put that in my calculator or figure it out in my head and replace it with an actual simple number. That's why I like to put my letter terms to the left and my number terms to the right. What is 180 take 50? It's 130. So why don't I write this equation again, but instead of 180 take 150, I will write something that is exactly the same as 180 take 50, which is 130. Okay, well now I'm very close to getting the answer. I know that 2 times my answer, 2 times x is 130. When you see a number followed by a letter, you can imagine there's an invisible times sign in there. There we go, tiny little times sign. So this really means 2 times x. 2 times my magical number is 130. I want to undo this and get back to my magical number, my mystery number, x. What's the opposite of multiplying by 2? The opposite of multiplying by 2 is dividing by 2. So this times by 2 on this side will turn into a divide by 2 on the other side. Do you notice that I write my divide by 2 as a fraction? This line and 2 means divide by 2. 130 over 2 as a fraction means the same thing as 130 divide by 2. And finally, now I can replace this. I can put this in a calculator or figure this part out in my head and replace that with the actual number. 130 divided by 2 is 65. So I'll copy down everything else and replace that with 65. And you might think this is a little bit silly, like why am I going to all this bother? But it is useful practice to be able to solve linear equations. We're doing 2 things at once here. We're learning geometry and we're also learning algebra. That is a very good deal on your education. I have some more examples in the next video, but I might pause it here, give you a little rest, and then we'll do some more examples in the next video. Bye everyone.